I'm Will Mars, founder and president of Endurica. 2020 has been a crazy year for all of us, but it's not all bad news. One good thing is that during this lockdown, we've made record strides in developing the Endurica fatigue solvers. Let's take a look at what's new. Perhaps the most important new feature is the ability to simulate the combined effects of aging and fatigue. There are lots of applications: tires, bushings, oil and gas. Whenever you have a long part life and long-term heat exposure, the mechanical properties of the rubber are going to evolve in a time-dependent way. So now you can deal with this using the Endurica DT aging feature. We've also added a cool new feature for tire analysis, a periodic results transfer feature that allows you to combine steady state and transient tire models. If you have IP to protect, or if you want to modularize your input decks for analysis, we now have an include statement, and we also have an encrypt feature. So you can go ahead and share your analysis files without having to give away all of the secrets that are in them. Another new feature is that if you're using our EIE tool to generate strain history, we've introduced a binary file format. It's half the size and 8 times faster to read. There are new output requests in our CL and DT solvers. There are more outputs supported in the results viewer. And finally, we've developed a real-time digital twin demo using Wolfstar's TrueLoad to pull loads off of a structure and then use our EIE and DT solvers to provide a live dashboard of damage accrual in real time. So let's unpack the new aging feature. What you're looking at on this slide are experimental results, aging experiments, for a model tire belt coat rubber. And these plots show how the mechanical properties of the rubber evolve. In the top left, we've got the fatigue threshold evolution with time. In the bottom left, we have the critical tearing energy, the strength of the rubber, how that evolves with time at the reference temperature, in this case 80 degrees Celsius. And then finally, on the upper right of the slide, we have a plot of Young's modulus as a function of time. All of these parameters can evolve with time, and so we need to be able to represent that in the code. The text box in the lower right is showing the syntax that you can use now in the Endurica solver to define the aged properties and these master curves in the Endurica DT code. We use tabular functions for all of these, so if it happens in the experiment, you can represent it in your simulation. The code calculates where you are on each master curve using a shift factor that's based on the Arrhenius law, which I'm showing on the left hand of the slide. This shift factor tells you how much faster the aging chemical reaction is running at each temperature. So for example, 1 minute at 100 degrees Celsius might react the same amount as an hour at room temperature. Now, in addition to a master curve, we also need to give the activation energy and a reference temperature to define our material for the aging calculation. Once we've done this, then the aging rate can be accumulated over the entire thermal history for each element in the finite element model. And on the right-hand side of the slide, I'm showing the equation that we use to compute equivalent time at the reference temperature on the master curve. So the end result of setting all these material properties up is a fatigue crack growth rate curve that evolves with time. So if you look on the curve on the left-hand side of the slide, you can see a set of curves that have been output from the code for various times. The black curve is the unaged crack growth rate curve, and then as you go from cooler colors to warmer colors, you're seeing the crack growth rate curve that corresponds to that particular aging time. Now, on these log-log scales, the changes to the crack growth curve seem very modest, but if you look at the size scale bar, you can see that the blue size scale bar is about a factor of 2. So the crack growth rate does go up or down, a factor of 2 or 3 over the aging life of this particular material. So when you take this variation into account, run it through the code, and calculate the strain life curves that correspond to these crack growth rate curves, what we find is a time-dependent strain life curve that I've plotted on the right-hand side of the slide, right? The x-axis is life, the y-axis is the peak strain. You can see that if you run the experiment at high cycle rates, 20 hertz or 2 hertz, 0.2 hertz, that all of the curves are basically the same, reflecting the fact that not enough time has been given for aging to affect the fatigue results. But if you run the calculation at lower rates, say 0.02 hertz and above, right, that's 50 seconds per cycle and slower, then you can start to see a significant impact, particularly when you have long life and a slow cycle rate. So for example, the red curve has a much shorter fatigue life for a given strain level than the unaged material. Let's do an example. This is a tension dumbbell, and it's going to be cycled from 0 to 15% peak strain, like we're showing on the left-hand image. Now, as we're showing in the middle image, one end of the specimen, the top grip, is heated to 100 degrees Celsius, while the other grip at the bottom is cooled so that it is maintained at a constant 0 degrees Celsius. Now, what we'll do is we're going to go ahead and cycle this specimen at the rate of 1 minute per cycle. And what this means is that about 10,000 cycles is equal to a week of exposure time. On the right-hand side of the slide, I've listed out the material property definition that we've made to define the aging properties of the rubber compound. In the aging workflow, both the stiffness and the crack growth properties depend on time. Endurica DT uses a co-simulation workflow that couples with Abacus to update stress and strain fields as stiffness evolves during the problem. What you're looking at on this slide are the distributions of, on the left-hand side, equivalent age on the master curve on the left. In the middle, you're looking at the final stiffness distribution at the end of fatigue life on the part. You can see that at the top grip, we've achieved the highest amount of equivalent exposure time, right, because that's the hot end of the specimen. And then finally on the right, we're showing the computed fatigue life taking into account aging on the specimen. And the fatigue life is predicted to be about 16,320 cycles, which is about a week and a half of time. You can see that in this simulation we're predicting that the specimen is going to break at the upper grip where we've been holding the specimen in the hot state. And just for comparison, if we turn off the aging and just do the fatigue test with material that keeps the material properties constant throughout the life, then we predict failure at the gauge section like we might normally expect. And we end up with a fatigue life that's much longer, about 800,000 cycles. So now let's talk tires. This is a workflow in Abacus that lets you generate steady state and transient tire solutions. For example, maybe you break in a tire with steady state rolling, then you impact a curb, and then you want to know how much damage the impact has done to the tire. So first, in order to do this kind of problem, you're going to need to obtain the steady state solution for the tire before and after it hits the curb. And you're also going to need an explicit transient solution for the times right before and right after you hit the curb. And so we'll follow the workflow in this slide to generate those finite element solutions, and then we're ready to do the damage calculation. So what we're going to do is use our results to follow two paths. On the top path, we're going to run the simulation using the steady state results, and we're going to tell Endurica to accumulate 30 minutes worth of damage, and then we're going to stop the analysis. We're going to do a periodic results transfer in Endurica to take the results, which since they were steady state, they're on a 2D cross-section, and we're going to copy the results over to a 3D model so that we can then take the results from the explicit dynamics solution for a 3D tire impact, doing the impact on the curb, and we can accumulate damage on that 3D model. And then finally, after we've completed the transient impact, then we can go ahead and use, again, the steady state solution to run out the tire to end of life. That brings us to step 10. And then now, for comparison, we're going to take the same tire, run it at steady state conditions all the way to the end of life. And what we can do is look at the difference between these two solutions as a way to measure the effect of the impact on the fatigue life. So we're going to compute a parameter D, which is basically the percentage difference, right? How much shorter does the life get because of the impact? This image shows contours on the left. This shows contours of maximum principal strain during the transient part of the solution, and anything above 18% strain is shown in red on that animation. In the upper middle, what I'm plotting, I guess on the rest of the slide, are color contours showing the relative difference between between the case where you have the impact and the case where you don't. So first of all, this is a side view of the tire. You can see that the shortest life is near the rim, where there's some damage that happens near the rim when you do this curb impact, and we lose 15 kilometers of life. You can also see front views of the tire. On the right-hand side, this is a front view looking at the tread. If you turn off the tread and just look at under the tread at the interior of the tire near the belt package, then you can also see the damage distribution there. And you can see there's a red spot right where you have this sort of bruise on the outside of the tire, and you have a red spot on either edge of this circular belt package. And at that red spot, we're losing 170 kilometers of tire life because of the curb impact that we've made. We've also plotted the results here on a tire cross-section. The way we did this was, after computing the 3D damage distribution, we searched each streamline, again, using our periodic results transfer feature. We've followed each streamline, found the worst damage, and mapped that back onto the 2D cross-section model of the tire. So again, that calls out the fact that we're seeing this rim failure mode for the tire. So just another example of what we can do for tires now. Many of our customers invest a lot in materials data, and they want to be able to share analyses with customers or suppliers, but they don't want to give away the expensive material properties measurements that they've made. So now what you can do is there's a feature in the Endurica HFI file. You can say include, you can put that in a separate file, and if you want, you can password protect that file. It will be encrypted, and so you can share without revealing information. If you want to know more about this feature and see a tutorial, I've given a YouTube link here. This is a list of all the new output requests that we've added to Endurica CL. So now you can get strain history components either in engineering definition or as a true strain. You can also get the corresponding stresses, and you can either get local strain history or you can get principal history. EIE has gotten a lot faster this year, and a big part of that is what we've done with binary file format. So EIE is our efficient interpolation engine. You can use it to set up pre-computed finite element solutions so that you can interpolate them to do fatigue analysis of very lengthy road load type signals. If you have very long signals, EIE can speed up your analysis by a factor of 10,000 or even more relative to doing the FEA straight up. And so the latest release with the new binary feature speeds things up by a factor of 8 times over the prior, and the file size is down by a factor of 2 for the same length of road load history. So since we aren't storing all the spaces and ASCII characters, we can just store the real numbers in a native binary format. So again, there's a link at the bottom of the slide here if you want to know more about EIE. So this was earlier in the year, but it is worth mentioning here that we've expanded the number of outputs that the Endurica viewer supports. Now you can get through the Hay diagram, you can get a view of the rainflow count output, you can get a plot showing worst events and identify those, you can get the damage sphere, you can get the strain history output, and there's others as well. So great stuff, and this brings us to our last topic, digital twins built on our DT and EIE tools. So what I'm going to show you next is a project we did with Woolstar's Dr. Tim Hunter. Check it out.
All right.
How you been, Tim?
Good, Willie. How you been?
Good.
How's the quarantine treating you?
Oh, well, I got my wild man look going here. Beard for the first time in 20 years. Yeah. Showing a lot more gray than it used to.
Yeah, I stopped growing my beard when it got gray. Okay. Yeah, and I've got the home hairdo right now. So.
There we go.
Well, hey, Will, over quarantine, I've kind of taken up a new hobby.
Yeah?
Pogo stick. I went out and bought a pogo stick, and I've been hopping around on the thing. And this pogo stick, it's got a rubber bumper on the bottom. It's got on the bottom of the thing, it's got a rubber bumper here. And
okay, that's right up my alley.
Yeah, and I'm thinking, wow, this thing is really going through all sorts of loading and fatigue. It'd be really cool to kind of figure out the durability issues with this little rubber bumper on the bottom of this thing.
Love it.
So is that something you could do? I don't know. Maybe I'm talking to the wrong guy.
Absolutely. No. If you could get me X, Y, and Z loads on the tip of that pogo stick, then I can process those lickety-split, and we can give you a dashboard that shows you in real time the evolution of damage on that tip.
You want loads? You came to the right guy.
That's perfect. That's just what we need. Let's do it.
We're all set, so let's go. Hello, I'm Tim Hunter, president of Wolfstar Technologies and the developer of the TrueLoad software, and I'm presenting this paper today with Dr. Will Mars of Endurica. So, part one. This is a high-level workflow on how to do load measurement with TrueLoad. So we're going to start off with an FEA model. So this is just a normal structural FEA model of the structural components of the pogo stick here. And what you can see here, I've got XYZ loads at the top of the spring for the pogo stick, and then down below we've got XYZ moments at the foot pegs, so you can see where the feet are entering moments into the system. And now that we've got all this, we can take these unit loads then, and the strain response from these unit loads, these 6 load cases, we can drive that into the TrueLoad software, and the TrueLoad pretest software is going to identify the locations and where to lay strain gauges. So here we've got 6 unit load cases, we've laid 10 strain gauges on the structure here, and now from these 10 strain gauges then, we can take now these strain gauge locations and bring them into the physical world. So now we're going to go in and we're going to instrument up the physical strain pogo stick with the strain gauges mounted on the pogo stick. And this, I should also mention that my colleague and employee Cindy Murphy did the heavy lifting here of doing the strain gauge placement here. So I thank you very much for that, Cindy. But we got those strain gauges laid on the structure. And now that we got the strain gauges laid, we wired that up into our data collection system. And the data collection system we're using is a very compact portable data collection system. That's called a DTS Slice Micro. So we're basically got a little data acquisition system here that we're driving these strain signals into. And then I went off and collected strain data on the pogo stick. So just coming here and using the pogo stick here. And from this event then, now we've got time histories of strain data at our 10 channels of strain. Okay. So this is us going in and measuring the strain. Now the whole idea here is that we want to take this measured strain and turn that into load, and we're going to do that with the post-test software. Now the post-test software is going to take the measured strain, it's going to multiply it by our correlation matrix from pretest to generate for us time histories of loads, and now that we've got these time histories of loads, the TrueLoad software automatically goes back into the FEA model, pulls out simulated strains at the gauges, and plots them against the measured strain. So what we've got here is the horizontal axis here is measured strain, the vertical axis is simulated strain for all 10 strain channels, and we've got a near one-to-one correlation here. So now we've got confidence that the loads that we're putting into the system are actually producing the strains on the FEA model, just like we were measuring them in real life. And so that gives us confidence that these loads are correct. Now that we've got these loads then, we're ready to pass those off to the Endurica, and we'll do that in a few minutes here. And then I can also go in and query where I had my reaction forces there, my restraint, and I can pull out the reaction loads here. So these reaction loads are actually what are going to be driven in to the TrueLoad Endurica software, because that's where the pogo stick is transmitting the forces. And then this is an operating deflection shape. So then in true QSE, we can then go through and basically grab a subset of the time domain here and generate an operating deflection shape. So here you see kind of the peak load area of the structure as it's going through an event. Okay. So now we get a full field operating deflection shape just from 10 strain gauges. So that's a pretty powerful thing. So here are the loads for Endurica, and then we just give those to Endurica.
This is part 2 of a workshop that Tim Hunter from Wolfstar and I have put together to talk about how you can use load reconstruction, how you can use rubber fatigue analysis tools to build a digital twin. This slide is a summary of the preliminaries that you need to have in place before we can get to the updating cycle for running a digital twin. And so one thing we need, of course, just like we saw on the last slide, is we're going to need the correlation matrix from TrueLoad, right? That relates the strain gauges to the loads and allows us to convert strains that we observe in the strain gauges on the frame to the X, Y, and Z loads. Now, we're going to want to take these X, Y, and Z loads and we're going to get them converted into strains in the nonlinear tip of the pogo stick. And to do that, we're going to have to somehow involve a fine element analysis. But what we're going to see is that the fine element solution is too slow to use in real time. So rather than doing that, what we're going to do is we're going to use a tool called Endurica EIE. EIE stands for Efficient Interpolation Engine. And what EIE does is it allows you to take a set of pre-computed fine element solutions and store them for later use in a very rapid calculation that captures the full nonlinearity of the part and allows you to get the strain tensor components for every element in the model for any combination of the input loads. We'll unpack this a little bit more, but so one of the basic things we'll need is to have run the fine element job that it takes to feed the interpolation process and get that all set up before we get into the digital twin. Another thing that we need to do to prepare to prepare the twin is to initialize the residual life. Right. So once we know how the rubber tip deforms under load, then I guess the question is before you do any actual cycles, if you have a standard load case, what would be the hypothetical fatigue life of the rubber tip under that standard load case? In this case, we're going to take 250 pounds is kind of the rated load of the pogo stick. So we'll take that as the standard load case for the pogo stick. That translates into I believe it's 1,100 newtons of vertical force with no side force. And so what we'll do is we'll run a simulation with just a single bounce for that load case, and we'll use that to present the initial residual life, which you can see here plotted on this contour plot. Now, the Endurica CL solver uses a procedure called critical plane analysis, and this integral that I've mentioned, where we integrate the size of the crack, that calculation is iterated over every possible orientation that a crack might take, right? So within any given single element, a crack potentially could occur in a number of different possible orientations. And what we do in our fatigue calculations, we calculate them all. You might say that the critical plane analysis is kind of a Murphy's Law type of principle, in that we're looking for the crack that's going to grow the fastest, and that's the one that we predict as controlling the fatigue life, right? So here's the workflow for updating the digital twin after we've set everything up and initialize the residual life. The guy on the pogo stick is jumping. There's strain gauges here that feed into a file. We record those. We pass those on to TrueLoad, where they're converted to X, Y, and Z loads on the tip of the frame, which we can then feed into our Endurica interpolation engine and convert the X, Y, and Z loads into strain history for each finite element in the model of the rubber tip. And once we've generated the strain histories, we can feed those into Endurica DT, where we can update the damage state for each element and finally present those. This is a lightweight dashboard that I'll show here in a minute. We can present the residual life at the current state, and we can also show some graphics showing the distribution of damage that's been accrued in the part. And at that point, then we can hit the update button and receive another file full of this information and start the process again and go round and round updating.
What I'm going to do now is just to give an initial test, let's do one standard jump, right? And what we would expect when we do one standard jump is that the residual life should decrement by 1 unit. So let's go ahead and do that. To do that, I'm going to hit the update button, and I'm going to go and find the CSV file that has the X, Y, and Z load history as a function of time. It's, in this case, a file called standardjump1.csv. I'm going to open that. Here we're plotting out the history. In that file, you can see the Y component of the load. That's the vertical direction. Y goes from 0 to negative 1112 newtons back to 0. So there's our 250 pounds. You can see that our residual life has decremented from 178.24 to 178.23, right? So we went down by 1 standard jump on the residual life. And go out and grab the data file that has 10 jumps in it. Again, no side force. You can see the green here. That's the FY 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So those are the 10 jumps. You can see that the process has just updated the residual life, and it dropped by 10 cycles, just like we would expect. So here we're feeding in standard jumps, and we're seeing that the metric of projected future hypothetical standard jumps is decrementing in the amount that we would expect.
So what about some real jumps? Okay, what about getting some of my real data, run it through?
Yeah, sure. Let's go ahead and we'll do your first jump. Bring that in, and we'll go ahead and run it. There's your first jump. You got 1, 2, 3, 4, 5, 6, 7, 8 jumps. None of these jumps were up to the full load, right? So at most you've got 828 newtons of downforce. So you're kind of, kind of lightweight compared to the standard.
I don't weigh 250 pounds.
Taking small jumps, little bunny hops.
Yeah.
So in all, that decremented the residual life by 2 standard jumps. And it's starting to, I guess if we were to keep doing this particular one over and over, I think we'd see this distribution starting to round out, because mostly this is vertical load. Your side forces on this were very small. We'll grab one of your, I forget
number 7. Number 7, I think, is I was finally getting good by number
7. I'll grab the PV one here.
Yeah, yeah.
So this one has what, 100 data points in it?
About, yeah, something along those lines.
So there you go.
You can see that I'm able to withstand the pogo stick a little bit more and keep my balance.
Right. So here you're almost hitting the full load, almost not quite the full standard load, but certainly you're getting 1, 2, 3. You're getting a bunch of these.
Yeah.
It ends up adding up to 5 standard jumps of damage is kind of what you ended up doing here.
Yeah.
So
well, it does more damage to me, I can tell you that. Okay. Well, that's very cool. So So just from some strain gauges, we can run loads into your structures here to get rubber in your digital twin. That's really cool.
Absolutely. Yep. Yep. It's yep. So.
Okay, great. Well, super Will. This was a fun project. A good way to spend our pandemic lockdown here to go through and kind of have this kind of cutting edge little technology between the two of us here.
This has been a lot of fun. This has been a lot of fun.
Okay.
Thanks, Tim.
Okay, great. Thanks, Will. Bye.
All right, bye.